Yep, as soon as you do.
Okay.
See if I can find you on my iPad.
All right. So, yes.
Now, we getting Blue on? Is he joining us? Do you know?
Oh, I haven't received any. I haven't received any communication from Blue.
Oh, okay.
Okay, but I just hit go.
Oh, if he's in the audience, then
Then hopefully we can get him on.
yeah, because I wanted him to talk about three phase
Okay.
basically.
All right. We'll keep an eye out for him in the chat. We are actually live at the moment. I'm hoping.
Oh, we. Oh, well,
Uh, so
just trying to get it up on another device so I can sort of watch the chat as well.
okay.
Yeah, it does say live. Are people? Is anyone there?
Yes, there are. There are a few
Oh,
people
well,
there.
some people are showing up.
Yes.
Awesome.
We're being described as failing tech weekly, which is, actually that's more me than you. That is more me than you. Hi, Mute
I'm not
Donkey. Hi, Faux Homer. Jessica G. Basic trigonometry is out there. Yes, excellent. I don't know who the Four Swordsmen are. I have heard. I have heard of them. Greetings, Clive Wells. But yeah. So they're horning in on this four men with shtick that I've got going, but with JL and Johnny O. Anyway, welcome to another great story, another great show of Watch Tony's Boogers. Yes. And we're yes.
I don't know where you got it from, Tony, but you have a reputation now.
For technical incompetence or for
No, 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 no. It's no. You should you should go into the medical world of people who have insomnia.
oh
Apparently, you help them.
yes that reputation. There are, however, risks. Without clinical trials, I'm worried that I could put somebody into a coma. Their
Okay,
dosages need
all
to be
right. Yes.
strictly controlled and measured. Their effects. Yeah.
Okay.
I've also got a reputation as the world champions for ums and ahs. I think I have
Oh,
the world record for the most consecutive ums and ahs in any single utterance. So I'm doing quite well as far as reputation is concerned. Anyway, how are you, Phil?
yeah. I'm well, thanks. Look, somebody's already complaining that I don't have a wrench, Tony.
Oh, well, yes, okay, I'll fix that. Put user in timeout. That's what I want. Okay.
Yeah, yeah. Well, it's sort of a busy time because of Christmas,
Yeah.
but as you know, we're all shut down at the university,
Mm-hmm.
so that's a good thing. And but there's still a lot of organising to do, and I've got a lot of organising to do for India because there's so much
Yep.
happening. Which there's some actually exciting thing that happens just 10 hours ago, about just over 10 hours ago, we had a satellite launch.
Oh.
Okay, so that's on the standard PSLV rocket, which is the standard one for PSLV, being Polar Satellite Launch
Mm-hmm.
Vehicle. Okay, so this is another polar
Yep.
satellite, and this one is a communication
Okay.
satellite. So that's just about 10 hours
Oh,
ago.
nice.
So it's now inserted into a transfer orbit, and then from there, one of my jobs, one of the jobs of the people that I'm involved with, is to put this into a circular orbit. So there's quite a lot of
Mm-hmm.
calculations and stuff involved in doing that. It's not. It doesn't just automatically go where you want it to go, and it's usually tumbling, and it shouldn't be doing that, but it does. Um, so we make sure that that the satellite's in its final orbit and doing what it's supposed to do,
Okay.
and that takes some precision work to get that done. Okay. Anyway, so that's what's happening. That's some pretty exciting stuff. The other thing is that working on trying to get that March date for getting the Chandrayaan-3 up. That's the yeah. So that's the next thing, and there's also setting up another team who are already working on the and they've been going for quite a while. That's the Gagaian team who are actually going to put India's first astronauts into space.
Excellent. Oh, that's
so there's only been one Indian astronaut ever who was on a space shuttle, I think. It was the only one, and then but now there's three people lined up. I think 3 backups who are going to 3 of the 6 of the 6 people training will end up being actual astronauts in 2022. So that's the following year, not far away.
Not far away at all.
People must be wondering, well, I mean, if the Americans are doing it, and you're sort of almost on a daily basis, going backwards and forwards to the ISS, and then they go to the moon, and they're preparing for all that. Why are the Indians, so far behind? And one of the things that flat earthers say a lot is that we're all in bed together. That they're not.
Yes.
They're actually, the competition is very, very, very fierce. Especially in ours, because I mean, our business is to put satellites in orbit. That's the main business that brings in money. Yep. Well, that's under severe competition at the moment from SpaceX and people like that who Americans who have so much money to throw at this stuff. So we're under severe competition. At the moment, we're still there because we're like the rickshaw. We only cost $10 around the corner. Other people charge $100.
Right.
So we're still in that vein.
Okay.
If all you can do is afford us, then we'll get our rickshaw rocket and get your satellite into orbit anyway. Okay.
Yes.
But we're certainly well on the way. Got a Mars mission.
Oh.
Certainly had since 2013, 2008, I think probably a satellite around Mars that's been going. As you know, there's a satellite around the moon. Chandrayaan's 2 satellite. And then this one coming up. So it seems like we're way behind, and yes, we are, and that's because everything we do is our own.
Yep.
All right. There's only one thing ever been bought, and that was the original rocket motor that was acquired from the USSR, and that was back in the early 70s. And then that was modified by a Indian hero called Vikram, Vikas, and Vikas designed the Indian version of this rocket, which has been used ever since on GSLV and PSLV rockets. Right. Lots. We're on the way, and this business about all the agencies work together and share stuff. Wrong.
Well.
Nothing could be further.
Well, I think you can confirm something for me, which I often bring up, is that NASA are forbidden by American law from paying scientists who aren't actually in America.
I'm not sure about the law, but it's certainly the practice.
Yep.
Okay, look, there are Western countries who do share information that definitely, like us, Australia. I mean, we're known. We do tracking of satellites and stuff. At Parks. Yep. In New South Wales, and Parks was responsible for the communications that happened between the moon and Earth in 1969. we're actually the ones who routed the image, the television images that came from the moon, that came through parts. So we had a lot to do with that particular incident, and many since, and we still do, because when you think about it, when the satellites and ISS and that come to our part of the world, we're the only big continent there. In this part, so in the right bang in the middle of the Pacific, so we're the only real continent there that's sort of halfway between South America and Africa. So we're in a very, very important function there, this part of the world. So we do have a lot to do with them, but certainly not a lot to do with the Indians and the like. But now Australia has its own space agency, which is located in South Australia. So they're building a pad. So we're going to be doing a lot of our own stuff in the future, and don't realise that this is actually one of the fastest growing industries on Earth.
And
so multi-billion dollars being poured into space exploration and space travel.
There's enormous potential economic rewards, and I mean we've already seen a lot the flat earthers like to ignore GPS, satellite communications, satellite-based weather analysis, sea level analysis, all of the various satellite-based technologies that have a very positive impact on their lives and the lives of millions of people. So, and while it's convenient for their narrative to ignore this stuff, it's actually occurring. So there's a lot of money in sort of further improving the situation, but we're doing. We are getting there. Fohammer in the chat made a point, and I do want to address it explicitly because it's something that sort of annoys me about the way science is depicted in film. In that he says, well, if you're, he says that you should be doing all of the tech stuff related to the streams because you can put satellites in orbit. So it's technical skills with satellite manipulations don't transfer automatically into live stream.
No, they don't. I reckon probably gaming does and stuff like that. I don't know even that.
But yes. So and Jessica says that I could bring down any of those satellites by singing in the shower. I don't often sing.
I reckon that Jessica has a thing for you.
I think that thing might be sharp and multi-bladed, but anyway.
Oh, okay, all right. I kind of wasn't thinking about that. That never even crossed my mind.
So we are here as advertised.
Right. Well, let's get on with the magnetism and electricity.
Yes. Well, I shall hide my ugly mug so that people can see your the glory that is your whiteboard. And
it has a reputation.
Yes, it does. Even better than mine. I also have a reputation for being drunk all the time. That's the other reputation I do.
Okay. It just
no. I'm far more boring than I am drunk. So okay. So there you go. There you are. You're on screen. You are.
Okay. Perfect. Okay. Or actually tell because my so far behind on my, so I can't actually tell
No,
if it's
we
if it's
can.
going to go
Yep, I
with
can
it.
see you in OBS and your full screen. You should be able to see that in the
Yep.
stream
All
now.
right. So if you have a look at what magnetism and so we sort of went through what electricity last time and it up for you, but then we'll talk about how it's essential to the transmission of electricity. So it's one thing to make the stuff, and then it's quite another for us to actually move it along and make it useful, so that you can plug your heater in or whatever else you want to. So let's have a look at magnetism. So as the first step, why are things magnetic is probably a good question. All right, and if we have a look at these two bars of here that of metal, okay, let's just call it material. Non-magnetic is where this crystalline structure of the metals would be higgledy-piggledy, so they go everywhere. There's nothing really structured about them. So a typical example is if you shear some aluminium, for instance, which we know is not ferromagnetic, so it's not going to become a magnet ever.
Yep.
So if you shear some of that, you'll notice that looking at it, that it's not actually smooth. Okay, so when you shear it, it's not smooth. It's not like cutting it with a knife, and it's nice and smooth. It does even look even crystalline, right? And it looks like the crystals are random, which is precisely that. And now even any a stone or metal can be like that, where the structures are just everywhere.
Yep.
And then in that situation, it has no magnetic properties.
Yep.
Okay, in other words, there is no magnetic field, if you like, that surrounds it that we can detect. However, if you find a way, and if it has the ability to line up these structures, okay, then it becomes a ferromagnetic material. So that's, and when we say ferro, because it's usually iron that does that, it has this ability to do that. So you line up these structures, and when you can line up these structures, then you're going to create a magnet. It can't happen with things like wood. It can't happen with things like plastics. There's all sorts of stuff. So while plastics and wood, especially plastics, can have electric fields, so we're talking about static electricity fields. All right, so electrons can attach to any object, and especially things like plastics. That we're not talking about the same thing. Okay, so when we're talking about magnetism, things that draw together, we're talking about materials, and as a result of that, create a magnetic field around it. Okay, so this is what we're talking about with here. Now let's just have a look at some other examples of this. For instance, over here, so if I were to draw this magnet like that, and usually a magnet like that's called a bar magnet, and let's call this end south and this end north, and then the magnetic field would be something like this, and would be coming out of north and into south like this. Okay, so it'll be out of north and then into the South Pole. So how do we know this? Evidence. We didn't just pluck it out of our butt like you do, flatties. Okay? All right, we can actually observe this.
We can,
with instruments.
Yeah,
we can observe its direction.
Can I? So one of the things that is quite widely used in earth sciences is the orientation of crystals in rocks and sediments, because they have a magnetic charge, and as they settle, they orient themselves in accordance with with Earth's magnetic field. And it's not just the north-south orientation; it's also the magnetic declination of where they're at. They have a tendency to preserve that angle. So this, these concepts that you're describing, which of course, you can observe and measure them in the laboratory under extremely controlled circumstances. But we use that understanding gained in the laboratory to better understand the world at large and its history. This entire chain of reasoning, what you're describing here, you're working from a very fundamental level of atomic structure and observable forces that we, and as you say, we have monitored this in laboratory conditions, and we extend that to the world at large, and we have a look around. It's such a fundamental process to science, but it seems beyond a lot of science denialists. Anyway, carry on.
Yeah. Well, I mean, let's say, for instance, they went out to the Pilbara or something like that.
Mm-hmm.
Where the ore magnetite.
Yep.
So magnetite Fe3O4.
Mm-hmm.
Okay. So magnetite is naturally magnetic, and it lives like this on the Earth as a piece. You can actually pick that up. In the old days, they called it a lodestone.
Mm-hmm.
So you can actually pick one of these up, and they will be magnetic. These. And how did they get like that? Well, like over millions and millions of years, these things which have ferromagnetic structures are able to align these structures up, and they align. Wherever they are, they align with the magnetic field of Earth. How that's not coincidence. But however, we know that the magnetic changed too. Okay, because of things that were once aligned and now are no longer aligned. They're diametrically opposed to the magnetic field of Earth.
Yep.
Okay, and also, as you mentioned, the declination. So these are possible. You can view these things. You can see that how it was in the past.
Yep.
Why? What's there now? We didn't pluck it out of our butts.
It's an important point that and we talk about flat earthers, of course, but there are other science deniers out there who are equally adept at pulling what they regard as science out of their rectums. Anyway.
So one of the things that I even mentioned last time, and how can you actually cause this to happen? Well, I showed you the coil, but I showed you the coil last time. So basically, if you've got one of these bars like this, okay, and then you wrap that bar with a coil, okay, and then you attach it to a source. Let's say you attach it to a DC source, okay? Then whatever you put in here, okay? Well, actually, let's just see in this coil. This will, as soon as you turn this on, you cause this to become a magnet because of the electron flow that's around. The electron flows are moving over here. This is negative and this is positive. Electron flows are moving through the circuit. They actually cause these structures to align. So the surface of this material, will become magnetic if it has that sort of property, like magnetic properties. So it's got to have the right properties in order to do that. You can put a piece of aluminium in this coil forever in a day. Okay, hell will freeze over and it will never turn into a magnet. Okay, but you put a lump of steel through there and it will immediately start becoming magnetized. And the other way of doing it, of course, you can get two of these, one magnet and one not magnet, and rub them together in one direction.
And most people will have done that.
Most
people will have done that with needles. You magnetize needles with you get a bar magnet, you run it across a needle, and to make a sort of rudimentary compass. Most kids will have done that experiment.
Yes. Yeah. Okay, so how is that not some evidence about what's happening? You can see that. Yeah. Again, just even at that level, you've got that sort of evidence, and then until you get to Gauss meters and stuff like that. These are all the things that are evidence that tells you what they are.
Yes.
So now try to think about how stupid it is to say that magnetism is the reason for gravity.
Yes.
Okay. Immediately now you know that it's not. Okay. So if you're listening to this and you're a flat earther, drop that nonsense.
Yeah.
Okay? Because you can see how stupid that would be. Okay. I can get a bit.
You can. Well, it's not it's not like I'm renowned for being necessarily the calmest at all points. Some people may have noticed me firing up on occasion. Yes.
Yeah. Oh, absolutely. I think I've learned my expletive repertoire from you, even at 66. Anyway, okay, so that's the basics of magnetism. But we're going to come to this because this is a really, really important part of this. Now, not only can we measure, do we know about that, we can actually quantify it. Okay, we can give this magnetic field some numbers. So in other words, because we can quantify it and because we can manage it, we can use it. So there's this famous formula here. F equals NILB. Okay, so what do we got here? We got F, obviously, is force. Okay, and force is force, right? So push against something pushes against you. Try to get two magnets and two north poles and try and push them together, and you'll see that there's a force involved in that. So you're required, not only you're required to put a force to bring them together, but now if you actually want them to touch each other, that's even a much bigger force that's required. And this force here, by the way, you'll notice gets bigger as you get closer to each other. So this is the force, okay? And then what we have is we've got N. Okay, and this is the turns. So this is really important, okay, the turns. Yep. The turns, remember we've got that bar and then we've got the loop around it like that. The amount of turns is important, okay? So that counts. Not only the square meterage of this loop, that's important, but the turns are important. Okay, so the turns, that's why you have generators that are huge. Okay, they're huge generators because they got lots and lots of this copper that's got turns around this. So it's necessary to make it large. So we've got I, which is the current. Okay, that's the current. So now we're talking about electricity. And we've got L. Believe it or not, the length of that coil is important too. Okay, so not only the amount of turns, but also the length of it. Okay, is also important. So you could theoretically make a magnetic field even if you didn't turn it right around the object, as long as you put it next to it. But it wouldn't be very effective, okay? And you need a lot of it. So by having the turns, you actually need less space to have a lot of turns, right? Because you're turning it. So one way to do that one of the compromises to make is to make the wire thin. Okay? Thin means more turns. So there's a compromise between thin, the cross-sectional area of the actual wire, which can carry an X amount of current, and also the amount of turns that you make. So you've got to find that balance between the amount of turns and the cross-sectional area. So therefore, you've got to carefully think about how thin or thick you want the wire to be for your coil. Okay, right? So length is important. And then finally, we get to recognize our friend Tesla here, okay? And this is actually the magnetic field. This is the magnetic magnetic field. All right, and this is in the unit. The SI unit is the Tesla. Okay, so there's a science behind this. All right, and then this again was not plucked from our butts. Okay, we actually did the science to verify all of these things. It wasn't by accident that it was discovered the length of the coil made any difference at all. Okay, all right, so I'm sort of tempted to ask you a question, the audience a question, to ask them a question, but probably only Clive will be able to answer it. But, well, okay, or maybe there's probably others there who can. Okay, now the other thing about magnets, and I think we sort of touched on this last time, so I'm going to rub this all off. Okay. Okay. The other thing is magnetic flux. So magnetic flux. So people often confuse magnetic flux. Okay, so magnetic flux, and the formula is phi equals BA. Okay. BA. And I just mentioned that to you. Okay, so this is the magnetic flux, is the amount of Tesla, amount of magnetic field multiplied by the square meters. So B is the Tesla, and A is meters squared. Okay, and phi. Whoops, I did it the wrong way around. That was theta. Okay, and phi is the magnetic flux. Now, let me see if I can get a lay understanding of magnetic flux, because most people have done this. If you grab two magnets together and you put them north pole to north pole or south pole to south pole, you'll feel a force in between them. You can't push them together, you know. And some of these very strong magnets that you can get, you absolutely cannot get them together. In fact, these are very dangerous, these magnets, because if you flip them the other way when you've got north to south and they smash together, they can actually smash your fingers. Okay, they'll come together that quickly, they'll smash your fingers. So this is definitely a force not to reckon with. Okay, and because this is such a magnificent, strong force, it's used for things like rail guns and stuff like that, which you mentioned last time. Okay, so when you kind of rubbing these two together, not rubbing, but when you're bringing these two together, you can just, as you slide them apart, it's you notice that it's got shear strength. Okay, in other words, it's kind of like, you know, you feel it together, and if you go like this, you can actually feel it, the shear strength of it. You know, it stops. You can go fast past each other, but then as you get close to each other, you notice that it stops. It slows down. You can't get it to move faster. So you can stop its speed of what you're doing. It requires more force to go past it. Okay, I'm not sure if I'm explaining that really well.
So shear is and you will notice this if you actually do get two strong magnets. So if you try and bring the two strong magnets directly towards one another, eventually the force you apply will be so great that they'll move, but they won't move straight towards one another. They'll deviate off to the side. Right, there'll be a sideways component to the force because, however precisely you try and arrange it, the two magnetic fields aren't perfectly aligned. They're circular. So there's going to be some asymmetry there in the forces, and that's going to force one of them off to the side relative to the other, or that both of them are going to move relative to the other. So you're going to get a lateral component of force, a shear, when you try to push them towards one another with a lot of power. It's going to push off. Okay.
Yeah.
I hope that was clear.
No, precisely said. And in fact, you just reminded me of something really important. I forgot all about this. Okay, remember I told you this formula, F equals NILB, the one that we just looked at before. There is another component to this for precisely the reason you just said, and it's called, and we can sine theta. Okay, all right, wrong thing, sine theta. So basically what this is saying, that the angle is important. Okay, so if it's completely parallel, then there's going to be no magnetic field, and magnetic field increases as you bring it towards 90 degrees in this case. So the angle is vitally important. That's what makes it impossible for you to bring them together like this, and quite possible for you to bring them together like this, and easier if it's just slightly like that, until it gets to be impossible this way. Okay, so 90 degrees is impossible, for one of these magnets. But if you want to bring them together, and it's also safer for you, by the way, if you do that, you try to bring them together and slide them along each other. Okay, all right, so that, because the sine of 90 degrees is 1, remember that? Sine of 90 degrees is 0. Okay, so bringing it along together like this, that's the best way to, and the safest way to bring those two magnets together. This angle makes a lot of difference. Okay, and it's really, really important in transmission. And if we could get Blue on here, he would be able to explain that into I want to leave that to him to explain that in terms of the of 3-phase, okay, instead of single phase. Anyway, let's carry on. All right, so what's important here is magnetic flux. The other thing about magnetic flux is it doesn't happen without movement. Okay, we need to have movement. This is really, really important for this next bit. Okay, so let's think about transmission now. So we decided, we discussed last time about the generator, and those who haven't joined, who weren't here last time in last week's technical debacle. Actually, it worked out it worked out quite well in the end, because we got saved. So anyway, what we decided then, what we spoke about, was how continuous electricity was created. Mm-hmm. Okay, and that was if you had a tube, okay, and you threw a magnet down the tube, north south, and you threw the magnet, and this had a coil around it. Okay, then connected to, let's say, an ammeter. Then that ammeter would register a current, and what would happen is, of course, it would just be one. It would just flick from here. It would just flick across to this side. Okay, so you'd get the current just move once. And of course, if you threw the thing up the other way, then the current would move in the other direction. Okay, so, and you can test this yourself if you just put a voltmeter on it. You can see that if you can flick the magnet down one side of the tube, it'll go in one direction. If you go, it'll go in the other direction. Okay, so you can test that for yourself. We didn't get it out of our butt. Okay, all right. So here we go. Now, the thing about it is that Tesla, being quite a fantastic engineer, which is really what he really was. So he never was a scientist. He was a great user of the science. He understood it quite well, and he understood how it works, and then became a great user of it. So when he spotted this, he thought, well, I could make some money here. And how could I do that? Because there weren't any. I don't think there were any flirts in those days. Perhaps there were.
No, I think Robotham is there.
Robotham. Yeah. Okay, we could have thrown Robotham's down there. We could have got them to one stand over here, another stand over here, and throw things down a tube. Mm-hmm. And you could keep lights going if they could get them to do it fast enough. But then I thought about it. You know what? You could get one of these flirts to just get on one of those bicycles, and put a dynamo in it, and they could just. But then you could actually get steam to do it, which is a nice way. So so all you need to do was change this from it became a mechanical problem now.
Yes.
Okay, so this wasn't a problem of how to create this electricity, but now it became a mechanical problem. How can you make this continuous? Which is precisely what happened. So before him, Edison and people like that worked on a motor which used what's called a split ring commutator. Okay, now we could bore everybody to death and describe a split ring commutator. And basically, its design of the split ring is to be able to make it continuous.
Yeah.
You could get the motor to move one turn like that, and then because it's got a split ring, it then forced the force that was already there because it had got momentum, forced it to continue.
Yep.
Okay, and one of the ways that you know this is sometimes an electric motor is not going, and you give it a helping hand. You turn it to give it a helping hand. All right, that's because now you're giving it momentum, and it needs that momentum to be able to get to the next turn, and in order for it to turn again. All right, so and sometimes this is not working correctly because your brushes in your motor are perhaps worn out. And they're not making contact with both halves of this split ring.
Yep.
Okay. So therefore, your nut motors, and sometimes you can make a motor just go a little bit further, even though the brushes are fairly worn out, just by giving it a helping hand, and then it'll take off itself. Okay. We do that a lot. Actually, I should have. I've actually got a demonstration. I might do that for next time. It's quite exciting. We'll actually build an electric motor here on this right here. Okay, so I'm going
to. It has been brought up in the chat. You won't have seen it, but people were very excited that I actually made a contribution to what was going on here. With my point about shit, because you're doing such a splendid job, and yeah, it would be very exciting to see an electric motor being constructed. So yeah.
Yeah, I think we'll do that. I think if you probably shine the camera at my desk, we can actually build an electric motor, and it's quite an exciting little thing to do. And you can actually do this at home. It's you could probably build it for, I don't know, $5 or something like that. You can, for less than $10, you'd be able to build an electric motor yourself. And it's quite a little, if you like playing with gadgets, it's quite a nice thing to do. So I'll show you how to do that next time. Okay, and we'll actually do some. Actually, we might extend that and actually do more experiments in some chemistry and blow up things live. We can do that because I've got quite a few interesting things that I've kept, in my days in the chemistry lab. So
fair enough.
Okay, all right. So now we've established that we can turn this as a mechanical problem, and we've turned it into a generator now, so that we can actually create this electricity. And of course, Edison did that, and using that split ring commutator. But then Tesla, he was a genius, actually, an engineering genius, and he thought, well, that's not really that good. And he came up with the slip ring commutator. Okay? And this was like the current went backwards and forwards. So that's what came up with alternating current. Okay? And then there was this big fight between which was the best one, and one of them killed an elephant, and I can't remember. I think the DC current people killed an elephant. Actually murdered an elephant in order to prove how strong DC was, which it is, okay? And one of the things about alternating current is it's alternating. It's turning off and on and off and on. Okay, so imagine what it does to your body as it's doing this through that. Okay, so the type of current that's used to kill people with this DC current, by the way. Okay, it turns everything, all of your insides out. Practically burns you alive in a hole that goes right through your body like the lightning does. Okay. All right. So enough morbid stuff. All right. So here we go. Here's our generator. So let's make a little power station over here somewhere. Okay. There we go. Oh no, it goes up. It goes thicker at the top, doesn't it? It goes more like that. Yeah, the cooling tower. Okay. So of course we need a cooling tower because we're making boiling water all the time.
Yep.
All right. Okay. So and then various buildings that go with it, and a big pole at the end, and then we've got our poles all the way to your house. Okay. Not sure if you can see this.
Yeah.
Okay.
Think it's coming up.
Okay.
Coming up fine.
Good. This is Tony's house. Notice how we all draw the house the same way.
Pretty.
Doesn't matter what.
Pretty much exactly what my house looks like. Yep.
Yeah. Well, we better connect with that. Okay. All right. So we've got all of this distance along here, and for people who live in Melbourne, for instance, this comes all the way from your lawn, which is about 300 kilometers away, or thereabouts of this transmission line. And one of the things about it, we're talking about energy. Okay, so what's going to happen is this: look, the actual. Remember I Flux and I spoke about the cross-sectional area. All right, so cross-sectional area is important because if the wire is thicker, it can take more of the current. You just think about it like a hose, like a water hose. All right, the bigger the water hose, the more water it'll get through. The more water will flow through it. Okay, think about a really huge hose is one at Wonthaggi where it's about 7 meters tall. Right, a hose. Okay, this is a big hose coming all the way from the sea because it's dragging in water into the sea, into the power plant, into the treatment plant. Okay, so all the seawater is coming in a huge hose. All right, so think about it like a hose. So obviously you want to have a pretty thick wire that does that, but the trouble is that you can't have it too thick, otherwise these poles won't be able to hold it up. And then you've got other problems. You know this word that flat earthers don't like? It's called gravity. Okay? All right? So gravity means that this wire won't be able to hold itself up if it's too thick. All right? Otherwise we wouldn't need a huge we wouldn't need things like superconductors. Superconductor meaning that minimal amount of resistance in this wire. Okay? So resistance is the amount of electricity that can be resisted. So in other words, there's things in the way stopping this water, if you like, or this electricity from going through as quick as it otherwise might. Okay, so we call that resistance. So this wire has resistance. It gets hot. You know something has resistance when it gets hot. Okay, so let's say, for instance, you've got your power board at home and you've plugged something in and you feel that the power board is getting rather hot. Well, this can be a dangerous situation, okay, for electricity in your house. And the reason is because you're drawing more current through that wire in the power board than that power board is designed to handle. All right, so it might only be a 10 amp board and you're trying to get 15 amps through it and you're going to heat it up. Now something's going to give. Either your appliance or the wire that's going from your appliance from that plug, or the plug is going to give, and something is going to get hot enough to cause a fire. Okay, so be careful about electric things that are getting hot in your house. Think about what that means. Okay, it means that energy is being dissipated through that in the form of heat. And if enough of that energy is dissipated for heat, there'll be enough heat to cause combustion. Okay, so that's possible. That's how electric fires can happen. All right, just because overloading circuits and stuff like that, or badly run circuits. Okay, so here we are, and so now we've got resistance through this. And if we started off over here at 70,000 volts, okay, by the time we get to the house, we might only have, 200 volts. by the time we get to your house. Trouble is, Tony, you're not the only house in the street.
What, other people want electricity too?
Unfortunately for you, yes. Okay? So, yes. So because you're not the only house in the street, it's pretty much useless if we've got 70,000 volts at the power station, unless this is called the Tony PhD power station. Okay? And it's all exclusive to you. Mm-hmm. All right? So you've lost all of this along the way, by the way, Tony. Okay? So what are we going to do about that? How are we going to solve that? Well, one of the ways is using a transformer. So as this gets smaller, let's say, for instance, we get to 50,000, we can actually up it. We can raise it up again. So it was back to 70 where it started. And as we use more friction down here, we can do it again, and we can do it again. And by the time we get to your house along the street, it's actually maybe 415 volts. And the thing about it, Tony, is that you don't have any of these kind of things in your house that are 415 volts. Your lights are only 240 volts. Okay, and if you're in America, it's only 120 or 110 or something like that. Americans are just different. Okay? They're different in everything. Okay, so if you're anywhere in our part of the world, in Asia or whatever, it'll be somewhere around about 220 to 240 volts. Yep. Okay? I'm not sure. I think that's the same in Europe, isn't it?
I think Europe might be 220 to
220.
Yeah, I think.
Yeah. I think it's just America who's one. They do their own thing. Every now and then they want somebody. They put a clown in as president. All that sort of stuff. just to have a bit of fun for 4 years. Anyway, okay. So it's 415 over here. How can we deal with this? How does all that happen? Well, it comes down to this thing called magnetic flux. Okay? So there's a core, usually, it would have to be a ferromagnetic thing, all right? And it's really just a metal bar, an iron bar that's sort of bent. Or you could just get a nice big flat steel and just poke a hole through it, okay, and make one of these. Yep. All right. Now, what happens is, on this side of it, we're going to make a coil. And let's say we put 10 turns. Okay? We put 10 turns on this side. All right? And then on this side, we'll put another coil. And this time we'll only put 5 turns on this side. So 10 turns on that side, so N equals 10. Might as well use the symbols correctly, because otherwise people think that means Tesla. Yeah. Okay. N equals 5 on this side. Well, what's happening is that because you induce a current over here, so you've got voltage. We'll call that V1, and we'll call that voltage V2. V2. Actually, it's actually called VP. Actually, it's called VP, and this is called VS in reality. Mm-hmm. VP means the primary side of this coil. Yep. Okay. So that's the primary coil. This is where the voltage comes in, if you like, and this is where it goes out. Yep. Okay. So the secondary is where it goes out, and the primary is where it comes in. So this is the primary voltage coming in, okay? So what happens is that as this going, it induces a flux. It induces a magnetic flux. In other words, magnetism moves. Remember, I told you how important it is to move? You see, this is the problem with flat Earth. They think nothing bloody moves. So if it doesn't bloody move, how can it create the flux?
Yep.
Okay, so here we go. So the flux moves.
Mm-hmm.
And as it moves, it therefore goes through this coil. So remember this, and you mentioned this last time. It's possible for 2 things to happen. One is, you can create electricity So electricity creates the flux that moves. Remember how important it is to move? Remember going through the tube?
Yep.
So electricity creates the flux that moves. So it's moving. That's caused by this primary coil coming in. It's moving. Where's it going to go? Well, it's going to go around this loop, isn't it?
Yep.
Well, when it gets to this coil, it's moving. What happens when you move a magnetic flux through a coil?
It induces an electric current in the coil.
It induces an electric current. How good is that? How bloody brilliant is that?
It is a spectacular piece of engineering. Mute Donkey makes the observation that it's sort of like having gears of different sizes to some extent.
It is. It's precisely that. Okay, but stop and think how brilliant it is.
I actually am going to confess I didn't know how transformers work. I've never looked at it, and I'm there thinking, that's really quite clever. It's really it is brilliant. That's the only word for it.
So now what we can do is we can say, right, okay, well, if let's say, for instance, we're here and we've got 415 volts on this side and we've got 10 turns, okay, and we've only got 5 on this side, we're going to get 200, aren't we? On this side. These are directly proportional.
Yes.
So, well, obviously people like Tesla thought about this and said, well, hang on a second. If I get less, what happens if I put less? What happens if I do it the other way around? And I put 207 over here. What will I get if I put more on that side? And guess what? He got 415 volts. How brilliant is that?
That's even better. Yeah. So
fantastic.
It is. It's a very it's a and without it, of course, large scale electrical generation across cities. The vast majority of our modern infrastructure depends critically on what is being described right here. And it's easy for people who don't know what's going on here to assume that it's easy, that it's trivial, that anybody could have worked it out. They could have worked it out if they just spend enough time on it. But it's not. It's not trivial. It's not easy. And we need to step back and just admire the. This is a fundamental layer of using electricity in power generation, but it is profound in its connection with scientific forces and scientific principles. So the whole concept that science doesn't know what it's talking about, that science just, as you say, pulls stuff out of its rectum. It doesn't gel at all. Anyway.
Yeah. So, well, that means that we now can get more voltage, but there's a cost to it, right? So just so you know, the people in the chat, that doesn't mean you can get free energy, all right? You can't just have little and produce more all the time, okay? All right, that doesn't mean, because there's a cost to it. You're going to lose energy in this setup where you're producing more. Okay, so there's a cost to it. You've got to pay lots of money for electricity to come from a long way.
Yep.
Because no matter how many, every time you do this and step up, this, by the way, is called a step-up transformer for good reasons. All right. All right. So every time you use this step-up transformer, and by the way, you see them around all the time. So the next time you drive past one of these things, you'll see this space-age looking place with all of these coils and humming and going on in there, and it's a big sign that says danger. Well, you're walking past one of these, only a bloody big version of it. Okay?
Yep.
All right, so that's exactly what this thing is doing for you. So it's stepping up this. In this case, it's all the way up here. It's going to step up. It's going to be a step-up transformer, and then at each house. So usually in your street, it's about 415 volts. I don't know what the Americans do, but certainly in our part of the world and in Europe, it'll be around 415 volts at the street, and then a step-down transformer on the pole will bring it back to the 220 or 240 volts that you need.
Mm-hmm.
But here is an important thing, and this is what makes this fight between direct current and alternating current. Now, watch carefully with this transformer. You see, because it doesn't always go in this one direction. Okay, and that was the important thing, because this voltage is coming in, it goes in both directions. It goes. Remember, I drew the graph last time. I'll use up this spot over here. Remember, I drew the graph. It goes from here. It goes positive, back to zero, negative, back to here. So this is positive and this is negative. All right.
Yep.
Okay. And the beauty thing about AC, and this is why Tesla actually got his name in a unit. I mean, that's a big deal.
It is a big deal. Yep.
Imagine if you did something called the Tony. You know?
There are things called the Tonys. They're theatre awards, but nothing to do with me.
Got your name up in lights.
Well, nothing to do with me. It's a different Tony. But
I'm afraid they haven't. I've never heard of the field.
You've never.
All right, but there you go. Probably
the chat are going to have some immense fun determining what award the Phils should be associated with. But anyway,
yeah, that's right. Yeah, I mentioned brothels, but I just pretend I didn't say that.
I think they were going to go there anyway, Phil.
Okay. All right. So anyway, so this is it. This is going up and down. So this is what's important, and this is what happened with the Americans. Okay, they couldn't make one of these.
Mm-hmm.
And this is where Tesla had them by the nuts. Okay? All right? Because they couldn't make this. They couldn't design this. Because they didn't have AC current.
Right.
They didn't have this. What they had was this.
Yep.
Okay? That's what they had. Okay? Or, if it's smoothed out, by the way, with capacitors, then it looks more like this. Okay? All right? So they had, this is DC. Okay? DC. And this is AC. And this was so much more superior. Because remember, the thing's got to move. If it only went in one direction, around here, then it, just like chucking the stuff down the tube, that would just be as if you chuck down the magnet down the tube, just in one direction.
Mm.
Well, it would go once, we'd get 207 volts, and then everybody go, well, what next? Thank you. That took about a second or less.
Yep.
Can I have more? Well, this is how brilliant Telstra was. Tesla, sorry.
Mm-hmm.
Telstra is stupid.
Telstra is pretty stupid. Most of our non-Australians won't really get the connection there, but yeah, they're a telecommunications company that we don't much like. But anyway, go on.
Yeah, Tesla. All right. So Tesla knew that if you used this voltage, this thing would go one way, and then as this switched back here, it'd go the other way.
Mm.
You know, the thing about it is, it doesn't care which direction it goes, as long as it moves, it gets flux.
Yep.
And that's what's important, because it's the flux that does the job. So it doesn't care. So it goes around one way, up this way, for that way, so right, reaches here, and then goes back again and moves. So it's continuous.
Yep.
So we get a continuous voltage from here to here. Whereas the trouble with I think it was Westinghouse.
Yep.
The trouble with Westinghouse was that he didn't have this thing.
Mm.
So he had your problem.
Yep. Yep.
practically a power station for yourself.
Yep. Which is okay for me.
So in other words, you needed just one city block needed a power station.
Yep.
Because you couldn't take this very far with DC current.
No.
By the time you got to here, you got practically nothing. So you had to start off with a lot and end up with nothing.
Yep.
There was no way in between to raise this up so that everybody had the same amount.
Yep.
In fact, with DC, the trouble was that the appliances, and I think this is where the 100 volts really came into being. It started off, the problem was probably there.
Yeah.
Okay, and that is because 110 volts was all they could give them. On average, on any household in this New York borough where it started all. Okay, so I think that's where that 110 volt history comes. The people in the chat can look up the history of 110 volts, and maybe they can tell us how come it's 110 volts. I don't know exactly what that is, but that seems to make sense to me anyway. So, anyway, just to round off this is how transmission happens. We've got this. So now, why do we have, for instance, these poles that go right up in the sky? And that's because there's a potential between the ground and the, let's say, clouds, for instance. So if static electricity is happening up there in the clouds, like it happened yesterday, then it's creating static electricity in the ground, and it must find its way to the ground. It must find its way to discharge that. Now, sometimes it can discharge between two clouds. So I think I'll just rub that off and just draw a picture of that. Let's say we've got two plates plus, okay, and we've got minus, is that these between these two plates is going to this way. Okay. And that as this builds up, isn't enough to keep them apart. And if they can find any way to get from there to here, they will. That's their job in life. Okay? So, of course, whatever is here that makes this closer, and that's you out in the field over here, and you making yourself a little bit closer to the ground than anywhere else. These things up there go, oh, beauty. Beauty. There's something down there. Who's that mug down there who's given us just enough room, just enough space between here and here for us to get to the ground? And they do, right through you, or a tree, or anything like that.
Yep.
Okay, I think that rounds up transmission.
Okay. So I had a presentation as well.
Go for it.
So
Everybody, you got your blankie?
Not you too, Phil. Come on.
I'm just joking.
That's okay. And this is where we're going to. This is where we're going to. Oh, there you go. That should. So this is where the technical expertise is going to be on display. Okay. So I may need to reposition this and then go over here. Okay, so I'm coming to, so today, as I promised, I'm going to be discussing bioelectricity.
Oh, okay.
So, which sort of comes on to what you were talking about. So this is there are a lot of crossovers here. So our story is going to start with Luigi Galvani, who did some early experiments on sort of using electricity to make frogs' legs spasm, as shown in the diagram here. So he was able to supply an electric current to the spine of a frog, and the muscles would contract, and they would move. Now, the theory at this time, at the time that Galvani was doing this, was that electricity was they didn't really understand what electricity was, and they kind of viewed it as some sort of fluid. You were talking about flow through hoses and making that metaphor before, and so Galvani came to the conclusion that there was something in the legs that was controlling the muscles, and there was some sort of source of fluid flow. And he actually ended up in a fight with Alessandro Volta. Alessandro Volta was not convinced by Galvani's reasoning, and he thought that actually there was some sort of electrical, that the flow of electricity was along the nerves, that it was coming from, that the impulses were coming from somewhere else. And in order to prove this, he actually perfected what's called the Voltaic Pile, the most basic form of battery that we know today. And there's an illustration of one there consisting of zinc plates and copper plates separated by brine-soaked cardboard that allows electrical flow. Now, people were able to recognize that nerves ran through biological bodies, that there was such a thing as a nervous system. They just didn't understand. They just didn't understand how the electricity, where the electricity was coming from, or how it was operating the muscles in turn. And while I'm on the structure of the nervous system, I want to point out a couple of interesting things. One of the beardsmen, J.L. Warren, the other week. I'm not sure if you know J.L. Phil.
Yes, no, I mean, not a lot about it, but I've watched some team.
He's
Stuff.
He's a very passionate and bright young man, and he got into a debate with about the existence of God, where sort of the perfection of human design was brought up. The perfection of biological engineering. And I have to say that if animals, if we are all designed by God, God actually needs some remedial engineering, because there's a particular nerve called the recurring laryngeal nerve, and animals use it to swallow their food. That nerve in all animals starts from the brain, goes down the neck around the aortic arch, and then back up into the neck to the larynx. And as you can see here, this very happy-looking shark or fish, that's actually a reasonable design. It's quite efficient. That doesn't. You can see why it's done that way, because that it is a slightly fuzzy picture. Sorry, it's greatly magnified. But the getting oxygen from the gills to the heart to be pumped around the body, that's not such a huge issue. But once you've got, say, a giraffe, suddenly the laryngeal nerve has to travel quite a long way, and it's not very efficient. Why is it that in order to swallow, a nerve impulse has to go all the way down the neck, around the pulmonary arch, and back up to the larynx? So here's a better sort of illustration of the course that the recurring laryngeal nerve takes. And if we think giraffes had it bad, poor old Apatosauruses and Brontosaurus and brachiopods had it considerably worse because they had the same feature. All vertebrates actually have this nerve structure. Rather than being sort of symptomatic of fantastic engineering skills on the part of the alleged creator, it actually seems more like we had a common ancestor for whom this wasn't a big deal, and now we're stuck with it because we can't get rid of it. And there's another example that I'd like to use that is also related to nerves, and this is the optic nerve. When in vertebrates, the same people who had such a problem with their recurring laryngeal nerve, the optic nerve is on top of the retina. So it comes through the retina, and the nerves actually overlay the retina. Not to such an extent that they block the passage of light to the retina, except at the point where the optic nerve enters the eye, and that's it. That image on the left is a vertebrate, is a standard vertebrate eye. That's what we've got, and you can see the point marked 3 is where the optic nerve is entering, and those nerve fibers overlay the retina, and that area marked 4 is a blind spot. That's where there's no retinal cells that can detect the light. There's no photosensitive cells. The image on the right is from an octopus. And you can see that God may have screwed up on the human eye, but octopuses don't have that problem. For any cephalopods, the optic nerve comes in underneath the retina, and they just don't have a blind spot. And if you're interested in sort of illustrating 2 points about the eye, here's a little test. Unfortunately, a computer screen isn't the best. But if you close your left eye and focus on the cross, focus exclusively on the cross, you need to vary your distance away from this image, but there will come a point where the yellow circle will disappear. And at that point, your brain will do something fantastic. It will replace the yellow circle with a red one, because your brain is programmed to try and compensate for your blind spot. That's why you don't notice the blind spot all the time, because your brain is constantly doing the processing necessary to compensate for this. So as a result of the optic nerve coming into our eye, we have a blind spot. But that engineering drawback is compensated for by processing in our brain. And this gets back to sort of the Flurfer logic that humans are perfect instruments of observation. And sure, we seem very good to ourselves, but when you're objective about it, actually, we're not so good. So, but getting back to the bioelectricity side to it, what's going on inside the human body that allows these nerve impulses to be transmitted? And it goes to the creation of potential differences across cell walls. So we've got a lot of sodium ions outside the cell wall, and we've got a lot of potassium ions inside the cell wall, and this creates an electrical potential. This creates they're both so there are different charge distributions inside and outside the cell, also the passage of chlorine ions as well across the cell wall. And the way that's done, there are particular proteins that are embedded in our cell walls that take ions and funnel them through. And there are two types. Of proteins. There are simple channel proteins, and they turn out to be very, very specific. You would kind of think that any sort of hole from the inside of the cell to the outside of the cell, that's shown on that thing marked protein channel. That shows that shows the just a channel down which ions can travel. And you would think that ions would be able to travel both ways, but it turns out that they're very specific. They're 99.9% accurate in the ions that they allow to travel through them. So there are ion-specific proteins that will allow sodium ions to flow out and potassium ions to flow into the cell. The other mechanism that is used are these ion catcher proteins that are shown in the three figures on the right. They actually capture an ion, isolate it from the extracellular space, and then release it into the intercellular space, or they can operate in the opposite sense. And so our cells are actually our cell membranes are actually very complicated in geometry. In order to preserve this charge, this difference in this electrical potential between the inside and the outside of the cell, and what happens. But because of the mechanisms involved, actually the human nervous system isn't entirely accurate. And unfortunately, I'm going to have to talk because I wasn't able to find a very satisfactory illustration for this. But the error involved with sending a nerve impulse is actually quite significant. More so significant that we wouldn't be able to do very precise actions based on the accuracy of that nerve impulse. And so the brain does something very, very clever. It doesn't send just one impulse. It sends lots of impulses in a bell curve. Oh, you are. There is a bell in science. There you are. There's a bell curve, so in that context, the bells cancel out. And so, well, the errors all cancel out in the bell curve, and so but the body also, so the muscle receives some warning of you're going to go at the peak of the bell curve, and then you're going to do your stuff. So so the way, and that allows human beings to do very precise elements of coordinations involving multiple muscle groups, and it's because of that sort of compensatory mechanism that humans are able to function in a lot of the ways they do. I don't know. This is a lot less technical than what you were teaching us about, but I found it quite interesting anyway. So I hope people did.
So one of the things that I just thought that this might interest you a little bit, and you didn't know about transformers. If you pick a transformer, that the core is not just one solid piece of metal. Okay, so one of the things that if we've got this, and then and I'll try to draw it in 3D like this. Okay, All right. So in 3D, and this is the core. Okay, so we've got some of it in here, right? Okay, so it was just one big lump of what they discovered was your coils around here was that more power loss. So you'd lose some of the power in a lot of the actual core itself has a job of magnetic flux. Okay, so magnetic flux moves around and goes back this way, around this way, back that way, because DC voltage in one direction, but only goes in one direction, then it'll stop the first time there. So how did they solve this thing power? And what they did was they said, well, create little current eddies. Little current eddies are like for instance, through here. So you got in this core, and a lot of them that way. So in other words, small of current. Okay, that was to try and make this as thin as possible, or as thin as. Of course, if you made it too thin, then carry enough flux in order to do the job. So they packed a whole bunch of these thin things together with an insulator. If you pick up a transformer and side on, you notice that it's layers. Okay, and the reason for those layers is to improve the efficiency of transformer. So you need it for an appliance. Everybody builds their own appliance.
Everybody does, yeah.
Okay, all right. But if you go to cheap one, that's going to take of these current eddies, or you're going to get an expensive one designed to minimize that. Now, okay, one of the other things about the wonderful thing about this transformer is this. Let's say we can shape it differently, and this time we'll shape the transformer like this. Okay, and we put one coil on this side. Well, there's no reason why we can't have 9 volts, 6 volts, 3 volts, and so on.
Yep.
So on this side you've got one lot of voltage coming in, and on this side you can have as many as you like.
Yep.
This way you can go to the shop and buy yourself a little transformer from the shop for an appliance, and you can switch 9 volts, 6 volts, 3 volts, whatever you like. Okay, how cool is that? All because of this little thing. Okay, one last thing about those current eddies. See, let's say this is the Earth. Flatties will automatically now dismiss everything that comes after this.
Yep.
Okay, so this is the Earth, and we've got a pretty good idea from the work that you do. Okay, that the Earth has a very, very thin crust.
Yep.
And then the mantle, inner core, and then the center core, and then the outer core. Yep. Right? Okay. Now the other thing is remember I said they're going to dismiss this out of hand. So first of all, this is a sphere, and second of all, it's got, we didn't need to drill more than 8 miles to figure this out.
No.
Okay, all right. We've got S&P waves and the like. Okay, so but it's moving. Remember this thing about moving.
Yep.
It's this movement that's causing these current eddies. So because this is a solid core, this one here is not a solid core, and this is because they're moving and moving against each other. That's creating this magnetic field.
Yep.
So this creates electricity, and it's this electricity, this movement here collects electricity, and this creates the magnetic field of Earth.
Yep.
Now, what does that magnetic field of Earth look like? Well, you see, it's another reason. It's another reason to know. It's one of those additional pieces of evidence that tells us Earth cannot be flat.
Yep.
Okay? For all these little bits of evidence that you put together is why the Earth is a sphere, apart from the fact that we've seen the bloody thing now. But even before we saw what it looked like, all these bits of evidence. So it's really like a bar magnet.
Yep.
So if the Earth is on an axis like this, it's really like a bar magnet that runs through it. And as a matter of fact, in this bar magnet, what we call the North Pole is actually the South Pole of the magnet.
Yes.
And what we call the South Pole is actually the North Pole of the magnet. Okay. And bar magnet, the magnetic field is going to go around it like this. Okay, and it's going to go out of the north, out of the north, because here, okay, so, and into the south, so it'll be in that direction. So that's the magnetic field. And the thing about it is, but for this magnetic field, there wouldn't be any life on Earth.
Yes, exactly.
Okay, it's because there's a magnetic field on Earth, this magnetic field, that there is life. And as I said before, this magnetic field has shifted and will do again one day.
Yep.
Okay, and probably destroy everything on it.
Well, so there's not really, that's the when you say destroy anything, the sort of extinction events aren't well correlated with magnetic reversals. But it will screw up a lot of our electronic infrastructure.
Screw up most of the stuff.
A lot of our electronic infrastructure is going to suffer badly as a result. But biological organisms are going to and
because they know it by
magnetism. That's right. So I just want to expand on this a little bit, sort of the relevance of the magnetosphere in deflecting, harmful radiation and shielding us from radiation that would kill us. We determine the conductivity of Earth's interior by using the currents that are induced in it by the solar magnetic field. Because the sun rotates with respect to the Earth every 27 days, something like that. And of course, there are 11-year cycles in solar activity, and you can use these different frequencies of change in solar electromagnetism to determine characteristics of Earth's interior. We can determine which currents have their origin external to Earth and which currents have their origin internal to Earth by spherical harmonic decomposition. And so we can work out the relationship between the induced current and the external current. There's just so much that science knows. People will, the flat earthers will instantly scoff, when you mention P and S waves. It works on exactly the same principle as an ultrasound. If you're happy enough to have an ultrasound to accept that ultrasounds are accurate depictions of babies inside a woman's body, then what's wrong with P and S waves being used to work out the internal structure of the Earth? And the reality is nothing. There's no problem with it. It works entirely well. But we can also use electromagnetic, and it turns out that there are similar. The conductivity structure of the Earth is very similar to. It has some structural relationship to the change in P&S waves that we observe, the acoustic properties of Earth. So, there are so many fields of science that we use that work together to let us know what's going on, to better understand the planet that we work on. And flat earthers, they're sort of it is difficult to wrap your mind around just how completely bankrupt their position is. Anyway.
I think so. The difference between flat earthers and just science in general is that we don't just go for one piece of evidence and say, well, then therefore the Earth is a sphere.
Yeah.
Okay. It takes a lot of different bits of evidence together for something to be called compelling, let alone to be called a theory or a law.
Yeah.
Okay. So it's got tons and tons of evidence. All of it's got to coherently come together for that to happen. Whereas if you're a flat earther, you can just say, it looks flat.
Yeah.
That was the sum total of your evidence.
Yes, and it doesn't, they've got no predictive ability whatsoever in any of their, they don't even have a hypothesis, so they can't make any predictions. They can't predict any distances. They can't predict any. All they can do is squabble over refraction. It's Clive Wells says that during magnetic reversals generally occur quite slowly, and he's right. They occur over timescales of thousands of years, from what we can tell. But there can be weakening of the electromagnetic field and sort of short-term deviations of it. It's a
We have yet to experience that. A total reversal.
Yeah.
So as humans, or recorded anyway. And so that'll no doubt happen.
Since I've taken aim at since we've taken aim at flat earthers, we've taken aim at anti-evolutionists. It seems only fair that the young Earth creationists get some love.
Yes.
We can use the chronology of what we can do. So magnetic reversals are. I might bring myself onto screen so people can see my the comedic value of my hand gestures. The magnetic reversals are recorded as stripes as the ocean floor spreads. You get these symmetrical stripes of magnetic polarity as you move away from the mid-ocean ridge. Now we can date those. We can radiometrically date those. And the young Earth creationists say, the radiometric dates aren't accurate. Okay, well, we can estimate their age another way. We can take the velocity of spreading and their distance from the mid-ocean ridge, and we can calculate their age that way. And it turns out that we get exactly the same number. Well, we get the same number within uncertainty. Magnetic reversals, and there are something like. There are many hundreds of magnetic reversals recorded in the I think it's like 180 magnetic reversals recorded in the currently available ocean floor. So if the Earth is only 6,000 years old, that means that the magnetic field has been reversing at a rate of about once every 30 years. That hasn't been happening. If there are any young Earth creationists out there, you're wrong. You're just as wrong as the flat earthers. So congratulations, well done you. I guess is what I would say to that. Anyway.
So Tony,
yep.
But I'm just thinking about next time, and one was that to
Yep.
go to the chemistry route and have a look at.
Yep.
The other one was to have a look at the Doppler effect. We talked much about the Doppler.
No, we haven't.
That's more evidence, because I'm really trying, because we're talking about this flat Earth debunking, we're really trying to how it is, what we do and why that thing. So let's stick with some physics.
Well, why don't we ask our chat, actually? So would people rather...
Chemistry or Doppler?
Okay, one for chemistry or two for Doppler. There will be a delay, of course. There's always a delay. But one for chemistry, two for Doppler. You guys get to tell us what to do. Fohammer, I have already been invited to debate Kent Hovind, but the person who wanted to do it wanted me to do it on their channel, and they are an unrepentantly intellectually dishonest young Earth creationist, and I saw no value in debating in that forum. If Kent Hovind wants to debate young Earth hypotheses. Okay, so
sounds
it
like
does
Doppler's
sound like
right?
Doppler's got it. Okay, so
let's talk Doppler and work out how sound works. Is sound, tie that sound to the Doppler. Have a look at the coming in, going out, and the Doppler effect, and then we relate that to how we see the Doppler effect in the it tells us whether if things are moving
exactly.
And in which
okay, and can be yes. So do you want to split that up? You do part of it.
Yeah, why don't you do spectrum and I'll do the sound.
Okay. Yeah. So let's do it that way. And that sounds good. Fohammer says Team Skeptic should be able to host it. I did sound out Team Skeptic. He is at a science museum this afternoon. So you should not think that I didn't reach out to him. I did. But I will try and get in touch. Sorry, I clean forgot to try and coordinate with Blue Marble Science. So I will try and get in touch with him about.
Yeah, if you think about the three phase, I saw. Yeah.
Okay. I've also got a friend who is a physicist, now retired, who may be interested in coming on at some point. But
that's good, because optics is a sort of field that would be good.
Well, in his bio he describes himself as a known associate of international arms dealers and consultant to professional killers. In fact, he. Well, he worked for the Military Science and Technology Agency, the DSTO.
He'll probably.
Yes, he probably will. We might be able to convince Clive to join us at some point.
Well, yeah. What?
Yeah. So we're not being rude, I don't think.
Pick with you, Clive.
So anyway. We'll but as you say, there is stuff to do today. Thank you so much, for being here, Phil. As I say, always educational. You will have, the people in the chat will have noticed that a lot of my understanding of sort of areas outside of my speciality is actually quite generic, and I tend to talk in generic conceptual terms. Whereas you've got a great technical aptitude that I really appreciate. Clive Wells does point out that next week is Christmas, so
He's right too. Yes,
so next week is and I had remembered that coming into today and forgotten it because I was so excited to be learning stuff off you. And the week after will be New Year's Day. So
Yes, yeah.
Let's rejoin here in 3 weeks. And okay. And so again, thank you, Phil, for a really stimulating and fascinating presentation. Thank you, everybody who's been in the chat. Really is exciting that anybody wants to listen to me, even for the little snippets. Listening to Phil, I can understand. And I hope everybody has a happy and, most importantly, safe holiday period. So please.
Yeah, absolutely. Yep. So, New Year, everybody.
Yeah, look after yourselves and spend some time with family and friends.
Okay.
Yep, take care. Cheers. Okay.